Now that we understand the value of behavior trees, it's time to create our very own behavior tree within Unreal Engine. We will begin by creating the necessary assets and then adding functionality to our AI controller to run the behavior tree automatically. We will finish up by creating our first behavior tree branch that will replace the random wander logic we created earlier with something much more flexible. Let's begin by creating the assets we'll need. First, create a new folder in Content Third Person BP Blueprints. Name it BT_assets. Open the folder and then right-click in the content browser, select Artificial Intelligence and then Behavior Tree. Name this asset BT_enemy AI. The BT prefix denotes this asset as a behavior tree. Once again, right-click in the content browser, select Artificial Intelligence and then Blackboard. Name this asset BB_enemy AI. As you may have realized, the BB prefix denotes this asset as a blackboard. The next step is to ensure that our AI actually uses this behavior tree. To do this, we need to open the AI controller. Within the content browser, navigate to the Blueprints folder and open AIC_third person character. Right-click in the event graph and begin typing event on possess. Drag out from the execution arrow of this event and begin typing run behavior tree. Select our newly created behavior tree asset from the BT asset dropdown inside this function. Compile by hitting F7 or the compile button on the toolbar and save this blueprint before closing the blueprint editor. Next, we need to ensure that the blackboard we created is associated with our behavior tree. Return to the BT_assets folder within the content browser and open BT_enemy AI. Moving over to the details panel, in the AI rollout, expand the behavior tree rollout and ensure that our blackboard asset BB_enemy AI is selected. Next, we need to create somewhere within the blackboard to store a target location which we'll later ask the AI to move towards as part of our new random wander functionality. We'll do this by creating a new blackboard key. With the behavior tree still open, select the Blackboard tab from the top right-hand side of the window. Now, move over to the Blackboard tab on the left-hand side and press the New Key button. Select the Blackboard key type of vector. Name this vector Target Location. Return to the Behavior Tree tab on the top right-hand side, and note in the Blackboard tab on the bottom right-hand side, we can now see our new vector. The next step is to create a new task that encapsulates all the logic of our previous random wander function. Like the old version, this task will find a new valid location that can be reached from the AI's current location. From the Behavior Tree window, select New Task, and then select BT_task_blueprint base. This will create the new task and open the event graph. However, before we do this, let's quickly organize our folder structure. Minimize the event graph to return to the main editor window and the content browser. In the content browser, locate the newly created task and rename it to BTT_find navigable location. As you may have guessed, the BTT prefix indicates that this is a behavior tree task. As it is a task, we should probably create a folder to keep it within, so let's do that now. Right-click in the content browser and select New Folder. Name this new folder Tasks. Drag our newly created task inside and double-click to open the Tasks folder and then double-click again on the task to return to the event graph. We will start by adding a new event. This event is called the Receive Execute AI, and this is the event that will be triggered by the behavior tree when it attempts to run the task. Add one now by right-clicking on the event graph and starting to type event receive execute AI. Within this task, we'll make use of the very same getRandomReachablePointInRadius function. The only difference will be what will execute this function and what we will do with the result. Begin by adding the function in the same way as before, by right-clicking on the event graph and typing getRandomReachablePointInRadius. The first piece of information we need is the origin, and luckily, the event receive execute AI gives us a really easy way to do this. One of the pieces of information it provides is the pawn that it is currently controlling. and we can use this to derive the actor location. Drag out from the controlled pawn pin and begin typing get actor location. Connect the return value of the get actor location function to the origin of the get random reachable point in radius. Set the radius value to 1000. Now we need to do something with the random location that is returned from this function. Unlike our previous setup, once this task is completed, all information contained within it is destroyed. What we need to do then is transfer this random location from the task to the behavior tree and to the blackboard. We can do this by using a blackboard key. Drag out from the random location and begin typing set blackboard value as vector. Note the second piece of information that this function requires is the value, the vector value. By dragging it out in this way, we've automatically connected the random location to the value. However, we still need a blackboard key. Drag out from the key value of the function and select promote to variable. Name this new variable target location key. In the My Blueprint panel, in the variables rollout, ensure that this new variable is set to public, as we will need to manipulate it from the behavior tree itself. Press F7 to compile this task. Before we forget, connect the execution pin from the event receive execute AI to the set blackboard value as vector function. Now we're nearly finished with this task. The only thing left to do is to tell the behavior tree itself that this task is complete. It's a very common mistake to forget to add this, and if we don't, the behavior tree will never consider this task as finished and will get stuck on this task forever. Right-click in the event graph and begin typing finish execute. Connect the execution pin between the set blackboard value as vector function and the finish execute function. Note that we have a bool that indicates success or failure. The cool thing we can do here is we can directly connect the return value of the get random reachable point in radius to this success variable. This means that as long as the function is able to find a random location, then the task itself can be marked as a success. All other outcomes will be considered a failure. Note that this is a big improvement on our first implementation, as we can actually tell if it succeeded or failed, rather than just having to assume that it succeeded. With that, the task is complete. We can press F7 or hit the compile button to compile the blueprint, hit Ctrl S to save the blueprint, and close the window. And with that, our random wander sequence is complete. Even with a tree this simple, we can begin to see the power of behavior trees. Just by ordering our task in this simple sequence, we've implied some useful logic. Remember that a sequence aborts when any task fails. So if the first task cannot find a suitable location, we don't even try to move towards it, as the sequence is aborted. Each one of these tasks has clearly defined states: running, stopped, and completed, including whether they were completed successfully or not. This is completely in contrast to our simplified version, which was essentially flying blind and had no idea about the status of anything it had been asked to do previously. In this video, we put our behavior tree theory into practice. We began by creating the behavior tree and blackboard assets for our project. Next, we saw how the behavior tree asset is where we will place all of our logic, while the blackboard acts as the memory for the AI. We associated the behavior tree with our AI character by adding blueprint script to the AI controller, instructing it to run the behavior tree when we start playing the game. Finally, we recreated our earlier random wander logic as a behavior tree branch, and saw how we could replicate this behavior in a much more flexible, easier to read manner using behavior trees.